So welcome to the department's most prestigious seminar. Uh, and this is the Mindlin lecture. Now, before introducing our distinguished speaker today, I would like to say a few words about the Mindlin lecture and about Mindlin himself. So the Department of Civil Engineering and Geomechanics established the Mindlin lecture in honor of pioneering contribution of Professor Raymond Mindlin to the field of applied mechanics. His research encompasses photoelasticity, experimental mechanics, classical three-dimensional elasticity, generalized continuous strain gradients, coupled stress theory, frictional contact, granular media, waves and vibration in isotropic, anisotropic medium, what it's called Mindlin plate theory, wave propagation in rods and cylinders, theory of electroelasticity, piezoelectric crystals, and crystal lattice theories. A member of the National Academy of Engineering and National Academy of Science, Mindlin received the National Medal of Science for Applied Mechanics and Mathematics in 1979. He had been awarded Medal for Merit in 1946 by President Harry Truman for his work in developing radio proximity fuse, a detonator for weapons used in offensive warfare that was a significant factor in World War II. ASC created Mindlin Medal in 2009. Now, when I thought whom to invite today, I remember the previous speaker was Tom Hughes. I see some equivalence between our speaker today and Mindlin, and maybe this is a bit indirect. Raymond Mindlin was a transformational innovator in mechanics. Bruce, on the other hand, who we'll introduce in a second, is a champion in transferring this mechanics knowledge to masses. And so let me say a few things about Bruce Engelmann. Bruce Engelmann now serves as a Chief Technology Officer at Hexagon, MSc. He is responsible for technology leadership, research and development, and product line related functions for design engineering with Hexagon Manufacturing Intelligence. Bruce is a thought leader and champion in computational science, multi-physics driven design optimization, incorporating advanced materials and understanding their complex behavior at all scales. He has led a variety of technology and advanced mechanics innovations in simulation software for more than 30 years. Bruce was elected to the National Academy of Engineering in 2018. Before joining Hexagon, he served as the Chief Technology Officer of the SAW Systems Simulia Corporation. He was responsible for growing Simulia's technology leadership position and guiding the company's technical software development in response to customers' long-term business requirements. He directed the development of Abacus Explicit for 5 years before taking the role of CTO about 20 years ago. Before joining Simulia, Bruce received his PhD in civil engineering and applied mechanics at Northwestern University in 1986. Following that, became a lead developer at Lawrence Livermore National Laboratory, as well as working as a principal in multiple startup companies involved in hardware and software development, including electric vehicle development at US Electric Car in the 90s. Well, his presentation today is entitled CAE for Manufacturing of Sustained Products, Trends, and Technologies that Will Power the Future. Bruce, the floor is yours.
Thank you, Jacob, for that very, very nice introduction. So like Jacob said, I'm involved in that last few miles in taking the best of computational science and computational mechanics and sort of bringing it to fruition with an industry. And it's amazing how far we've come over the last 30 years. And I'm gonna, in this talk, I'm gonna look back a little bit at things that have happened, and then I'm gonna look very forward and try to talk about the opportunities. Even though these disciplines in computational science and computational mechanics have matured so much, there is still so much yet to do. So I'm going to be talking about trends, I'm going to be talking about sustainability, and I'm going to take a few deep dives on manufacturing and simulation. So first of all, I'd like to talk about the roots of the company I work for. I joined Hexagon about a year and 3 quarters ago. I was at Dassault Systems for 23 years. I made the move to Hexagon because I really saw the promise with really bringing the real world and the virtual world together. And Hexagon is a company that has a lot of very, very important assets and technologies in the hardware space and also in the software space. But the part of Hexagon that I play in is design and engineering, which is simulation and CAE. And in fact, this is a fairly new division at Hexagon for the last 3 years. They acquired the MSC company. So I'm going to go back and talk a little bit about MSC for just a second. MSC, you probably know MSC through Nastran. And actually MSC was one of the first 10 software companies in the world, right? This is amazing, actually, if you think about it. But that shows how old CAE is in some ways, right? It's still around. And Hexagon now is breathing new life into all of the technology. Now, MSC goes way beyond what was then Nastran, but this was something that we just published, basically, which was a history and a timeline of mechanics, starting back from Jacobi and Euler and Lagrange, and the first programmer was a woman, which is really interesting, in 1800, and people like Fourier. And then moving into with Dick McNeil, right, who's really founded MSC Nastran, so consultancy with NASA, and then some of the big influencers in engineering, mechanics, and finally the trends and other things that have influenced the development, and then basically the products and systems that influenced by Nastran. Now, what was not on here, interestingly enough, and I just saw this, was all these mechanicians that were in the early and mid-century that really laid the groundwork for everything we're doing. And these people, before computers, we were able to simulate on computers, before the whole computational science came about. That the greats here actually gave us the tools and the mechanics, the strong science and math behind what we've been able to animate on computers to really make a difference in engineering complex products. So that's a tribute to Dr. Raymond Mindlin. So Hexagon. So let me tell you a little bit about my company, because this will sort of frame the things I'm going to talk about. It's a very, very diverse set of holdings. I actually work for a division called Manufacturing Intelligence, which has design and engineering, which is what I'm principally looking after. And it also has production software. So Leading is the #1 in production software, everything from NC machines to additive manufacturing to die design, and also metrology. So metrology, this is hardware, about $1 billion business in very, very advanced computer measurement machines, optical scanning, tactical scanning, all kinds of measurements. We also have many other divisions, including this is really manufacturing, discrete manufacturing, but we have PPM, which is for facilities like refineries and processing plants, a full, basically, digitalization of those kinds of plants and assets. In fact, PPM includes the old Intergraph CAD, which is used for design of those sorts of systems. Smart mines, agriculture, autonomous. We had technologies, including intelligence and even autonomous driving simulation, which actually is in my division, autonomous driving. Smart buildings, construction systems, again, keep track of data, providing planning and CAD systems that go along that, and also things for smart cities. Very, very diverse set of holdings and technologies. So this is basically kind of bringing to life what I just showed you on the last slide. We have divisions in the geospatial, which can map out, basically, you think about Google Earth, those technologies, we provide those to the OEM, those kind of technologies to companies. We make 9/11 call centers. We see some other interesting things, make a lot of things for civil engineering, right? Civil engineering department, and BIM and AEC. And along this way, I'm seeing maybe I need to minimize this. Here is this little part which is CAD and CAE. And actually, CAE is a little part, but simulation and computational science actually can span a lot of what's here. And that was the point it was making. If you just limit it to CAE, it's very limited. But what you can do with the kinds of things that we develop and that we invest our time in is pretty incredible. Okay. So now I'm going to talk a little bit about hardware for just a second, because this was something that I've learned about in the last year and a half, 2 years. It's amazing how we used to think about testing. Simulation is going to get rid of testing. It's so interesting because that was the trend. But like everything else in life, things circle around, right? Things always circle around. And now, and think about testing, that it's not about testing, it's about sensors. You can measure everything. And these are just the kinds of technologies that Hexagon has for sensing everything from LiDAR to radar to tactical sensing to being able to break down CT scans and those kinds of data. We have for instance, one of the brands we have is Leica. Think about Leica for cameras, but Leica makes the devices that you might see that you think, okay, it's a security camera attack. But those things actually can have LiDAR, so they can map out 3D point clouds and continuously send data, right? And then they also have cameras and audio sensors and temperature sensors. We're all wrapped in those kinds of packages, right? We have tools that you can walk around the room and everything and get a 3D topology of the room. Lots and lots of ways to measure data. And this is the new oil. Data is the new oil. It's not going to replace what we do with physics-based modeling. But what we need to do is we need to embrace this. And those are going to be a lot of the new opportunities. Let's talk about changes that are going on. 20 years ago, okay, this is just one example. This slide actually now I'm stealing from the CEO of Hexagon, Ola Roman, a set of slides that he gave, very high level slides. 20 years ago, the world was in paper. I just went to Starbucks on 75th Street, right? You go to Starbucks, you see the New York Times, you see the Wall Street Journal, you see all those things. 20 years ago, you had the rack, right? Newspapers were starting to hurt just a little bit then, but that was the way you consumed the news. Now you go into Starbucks, you won't find anything. There's nothing, right? The world was in paper. So let's look at all kinds of things that were going on. 20 years ago, this is kind of the layout of what you did. You went to the store. There was logistics with trade trucks and trains and ships and transportation, mainly obviously IC engines. And life was moving ahead. Lots and lots of developments to the year 2000. We had this thing called internet, which I remember back in the Clinton War times. The internet superhighway. This is like the brand new thing. It's going to open all things. And like everything has a hype cycle, the internet had its hype cycle, and then we had the crash in 2001, the .com bust. But obviously, this is the thing that's basically shaped the way forward for the last 20 years after the hype cycle. So let's look 20 years forward, and all of a sudden, there's a lot of things that have changed, and the pace of change is incredible. The pace of change is accelerating. This is a really, really important driver for digitalization. It's just things are changing so quickly. So from the way we consume, for instance, for TV, right now we do digital on demand, and we stream movies and we stream music, right, and we stream gaming and socialization. We shop digitally. I mean, this has even been accelerated with COVID. I mean, I'm hoping that we get back to the brick and mortar, but my guess is that the brick and mortar stores eventually will be more like experience places where you can experience things, but you're still going to work sort of be a combination of both the sort of more autonomous and the interactive experience. The way we shop is different, right? The way we shop, and COVID might even accelerate the way we shop. Groceries, logistics now, where we're looking at and logistics and transportation. We're now looking at electric cars. So I was in the electric car business. I was involved in a startup in 1993 to 1995, a little bit too early. It was a little bit too early to be in that business. And now look at where we've come over the last 20 years. Even though I think the number of electric cars, for instance, is less than 5% of the cars that are out there today, maybe electric and hybrid, maybe it's a little bit more than that. But the amount of the investment that the OEMs are making, auto OEMs, is well over 50% in electric propulsion. So that's the future. That's the future of vehicles. And this all happened in the last 20 years. Okay. All right. So catfishing. So I'm 61 years old. I'm an old guy. I have to live vicariously for my 21-year-old twins. I don't even know the term catfishing. Apparently, it's a very popular term. Usually, it applies to online dating. So, you know, people have that really nice picture from 10, 20 years ago. Maybe it's a little photoshopped, and they're online dating. They have sort of a persona, but it's not really exactly what you said, right? It's not really up to date. And in fact, I just changed my LinkedIn picture. And actually, the picture I'm showing is up to date because it was taken in Belgium just a month or two ago. So that's actually an up to date picture. Now, I'm not going to say it wasn't Photoshop, but it is an up to date picture. Okay. So why did I talk about catfish? Okay. So this is Manhattan in 1931, and this is Manhattan today. And this is electronic. This is a picture, and this is digital. This is an image that can be continuously updated. And imagine now when you have an asset and it's electronic and it's not well, you don't know its pedigree, you don't know when it was developed. If you base your decisions on this instead of this, you're out of here. There's nothing you can do. And that's really what digitalization is. When I walk into the airport, I'm an old school guy. I'm finally paperless. When I travel, before COVID, I always had a copy of things in paper. I don't do that. I just have multiple devices and I'm hoping they always work. But now I have I'm living in Atlanta now. I have my Delta app. And one of my colleagues, Andy Columbi, explained digitalization as follows. He had the boarding pass. He even had a boarding pass, a picture of a boarding pass on your phone. That's an electronic document, that picture, a PDF picture, whatever it is. Okay, but when you have the app, it tells me if I've been upgraded. It tells me if the plane's arrived. It tells me even when I'm sitting there and I'm waiting for it. It tells me, okay, you're main cabin 1. I can't fly business class with my company, main cabin 1, but you need to get on the plane. And that's what digital is. That's a really good explanation of what digital is. Okay. So this is really why industry in general needs a smart digital reality. And that's the move to digitalization. So what we're talking about with digitalization is really fundamentally finally bringing the world and the digital world together. Productivity, efficiency, and stability, which will then amount to cost control, output, and performance. So what are we talking about here to get a little bit more concrete? So on the real world, we have all these kinds of sensors. We have measurements, we have data coming in all the time. You need to capture that data, right? You need to be able to capture it. You need to cultivate it, curate it, and then it needs to be transferred. That's why you hear things about edge computing and cloud computing. It's very important to do that. But then on the back end, then what do we do with that data? Today, we're just bringing data like crazy. And some of the companies are being able to take advantage of it, but it's really just become. The idea then is you should be able to visualize that data, right? Review it, analyze it, and this is where computational science and computational mechanics comes in. Model-based combinations of physics and physics reality and digital reality and coming together. And we get several examples in the talk of this kind of thing. Then once you do that, you can define actions. First, you have what we call descriptive analytics, right? And then the maturity to predict it, and then prescriptive analytics. But you figure out what actions, and then you have take actions on that. So let's give some examples that you'll see are quite diverse. The first one, discrete manufacturing. So discrete manufacturing, you're measuring things from the asset, from the machine, and the work cell. You have all kinds of sensors. You can figure out what that machine is doing at the time. And then you can also look at what actually happened with the part. So you can use tactile or optical scanning. You can scan velocity, and you can measure all that kind of data, right? You bring that in, and you can understand where things are going wrong and where you need to make improvements. And basically using models, and it's not just geometry, it's physical models that you can understand how fatigue is affected by porosity and how performance will be affected. You can define those transfer functions, you can use that data, and you can then define what you need to fix in the factory, how you can make things more efficient, and then come back and take those corrective actions. Now, I'm going to use some acronyms here. EAM. It's a little bit of a new acronym for me. It's Enterprise Asset Management. So that's the kind of thing where in a factory you're looking at about managing those kinds of assets. You've probably heard of ERP. The way I look at that is a factory, you have a control volume. So the boundary conditions there are the resources coming in and the products and resources going out. So that's what ERP systems are. Enterprise research planning, PLM, product lifecycle management. And then inside the factory, so I have my control volume. Inside the factory, I have manufacturing execution systems, which are enterprise systems, and also MOM, which is manufacturing operational management systems, which are like MES systems. Lots of acronyms too there. Industrial facilities are the same thing. So you have the reality and then you have the digital reality. In aerospace, they used to call this digital line. So like we have assets that you can basically have, you can think of it as a CAD drawing of, not a CAD drawing, a CAD file that contains everything on a square mile refinery. And then obviously, even for things like visualization, you've got to look at a square mile and then you might come down and look at the junction of two pipes coming together. So it's kind of an incredible scale problem. That's a geometry scale problem, but it's kind of the same thing. You have to use multi-scale techniques, even in the way you look at data, and then, of course, buildings and infrastructure. Are you starting to see a trend? So these are very, very different sectors, but you can apply the sort of parallels between the virtual world, the real world, and the virtual. Now, buildings and infrastructure is an interesting one because a lot of construction is still done with 2D drawings. But in the end, and that's the way it works, which is kind of okay, but what you need to do is you need to relate those 2D drawings to 3D representations. And then you can really understand everything that's going on. And then with all the different sensors and measurements, then you can go ahead and you can analyze that data and then take the appropriate actions and bring them back into the work site. Very, very challenging problem. Right? It's a little bit out of line, sort of my scope, but you can see that you can apply the same principles. Another one is safety, security, and surveillance. Remember I talked about those Wi-Fi devices. Let's say a VLK360, mount it can maybe either 30 feet or 30 meters. You can look at the area and it can basically a LiDAR scan of what's going on in 3D. Now, the point cloud itself, because it's 3D, is only so accurate, right? It only has a certain amount of resolution. It's got to pump this data through. It's continuous, right? It's continuous with updating. But you also have 4 cameras on it. So now you have 2D images, right? So now you take the 2D images and you put it together with the 3D data, which gives you depth. Now you can use AI. So say you're on this is relevant for New York, you're using the subway, you want to be safe. Somebody leaves a suitcase or something like, or a package there is unattended. Those are the kinds of things where you use labeling, training your AI, and then the image recognition and all the other things that, and you can figure out that may be and then immediately somebody can notify the situation. Right? That's what digitalization does, and that's what connecting information does for you. In the future, who knows? Lots of things going on. What I would say is that autonomy was one of these things that went through a hype cycle. We have autonomous software in my division. I think that before maybe 2 years ago, people were still thinking that we were going to reach level 4, level 5 autonomy, which is a total of 6 levels in 5-10 years. And now that's sort of backed up. And now they're talking about getting to level 3, which still involves a driver and a third, but things like ADAS, so assisted driving, you're going to see more and more of that. Now, where you're going to see autonomy are things like logistics. You're already seeing it in factories. You're already seeing it in companies like Wayfair, Amazon. Unbelievable what they can do with robotics and logistics. So a lot of the autonomy next years is going to be in logistics, where you can deploy it in a safe way, right? And then that will lead to more autonomy on the streets, like people would envision. Okay, let's look a little bit at manufacturing, and since we're talking about economy, there's a certain maturity model that you have to start with actually getting the data, right? And then you need to improve the visibility. Then you can start to use, like I said, prescriptive or predictive analytics, and then prescriptive analytics. And then you can imagine starting to learn from those things and self-improvement, and finally autonomy. So this is a journey. And as a software provider, we need to think about this, because it's not something that we can just say, okay, here's software, now you have autonomy. It's ridiculous. It's a journey that the tool providers and platform providers need to walk along with their customers. So we need to have platforms that you can build from doing things that are very manual and very discrete and siloed to more automated and connect the data. And then over time, you have these little pieces of automation, and you can start to string those pieces together. And then once you string these pieces together, then you can have a system that thinks on its own, which that doesn't really happen. But that's where you get to autonomy, where you can actually react to things. So it's a journey. So in the future, I think the kinds of technologies we're going to use are going to have to take people through that journey. And it's going to have to be companies themselves that develop these things. It's not going to be the tool providers. We just have to provide the basis vectors for people to do that, right? Let's talk about a few examples. Additive manufacturing. In the aerospace business, basically, 72% of the companies are using additive manufacturing for prototyping. Okay, and 44% for repair and 43% for R&D. Okay, so what you're seeing in the aerospace companies today with AM, which is a major driver for sort of the high end of additive manufacturing, alloys like titanium. This is kind of a big thing. It's mostly about not really critical parts, more like, I think an example, like building a large trackable plane, you have brackets, something like that. Kind of like the aircraft. Things that are behind the scenes, I don't really care how they look. They have certain kinds of specifications and frozen regions, if you want to call it that, certain kind of that, but the rest of it can be done through functional design, right? And then additive manufacturing. So right now, there's a pretty big boom. Again, there's a little bit of hype. There's a lot of hype in additive manufacturing. It's going through the hype cycle, and we're got to come back down before we plateau. But this is where there's no doubt that it's going to keep going, and then you're going to build on there. So the aerospace industry is embracing this, looking at about a 20% growth rate of the kinds of things people do with additive processes. Kind of technologies you want generative design. You need tools to be able to simulate the manufacturing process, to be able to plan them, and then be able to measure the results, monitor those assets. And so I'm going to now talk a little bit about this sort of feedback loops, because I think the feedback loop that we're all pretty used to is design feedback. This is what's been maturing over the last 30 years. Unbelievable how CAE really has developed, and how it's now really an integral business process in every way, right? And so we companies themselves, especially the bigger companies, can really tighten this loop between the actual design and manufacturing. So that obviously with additive is a very, very important point. You need to optimize something for performance, but you also need to optimize it for manufacturing. Okay, this is one of the key things. Additive will never really be accepted until we can be much more predictive, much more reliable with our parts. We have to certify them. There's lots and lots of work that has to be done here. It's an iterative process. It needs to be automated. It's difficult. Lots and lots of research in this area, and it's feeding into the kind of tools that we're providing for our customers. So that's an iterative loop. And then you come back here, and then when you go ahead and now quality, it could be metrology, it could be MRI, it could be any kind of thing. You're looking at the quality of parts that are coming out. This also needs to feed back. This is data driven, right? This is hardware and data. But then it can feed back to the actual design, and also feed back to the manufacturing process, right? And finally, there is a service life, which would be called like an operation, where I can actually look at things in the service, measure how they're doing, and again, feed that design, feed that manufacturing process, and that's where the visualization and the connections come in. Let's skip the video here. Offshore wind, something very different. Now I'm talking about sustainable wind power. It's on fire. All over. It's growing. People are really understanding how to make it efficient. There's still lots and lots of issues about lifing and operating the wind turbines. Typically, gearbox and generator failures, they do happen, and they can bring even if you have a really sort of cognizant operator, they can be down for 2.5 days, which again, if you're managing lots and lots of assets, this is a problem. It's very, very expensive. So there's a great opportunity. The 66% of the failures are due to the nutrient and generators, and there's going to be a lot of growth of using wind power in the U.S. This is a great opportunity to bring computational methods and digitalization to the table. So one thing I can say about these problems is companies like let's say like GE or other people that make wind turbines. Even when it comes to gear trains, they're doing multi-body dynamic simulations. They may need to do millions or even billions. It's incredible the number of scenarios that they have to work out. Also incredible the size of these gear trains. I mean, we're talking about, you think about a gear train, it's a small little box like that. On these really large span wind turbines, right? You have, it's not the multi-body dynamics that your brain follows. I'll tell you, you have to be able to take into account it's definitely flex body, right? And even more than that, even the contact is really hard to deal with bearings. This is like really big stuff. There are tremendous moments and torques on these kinds of technologies, and they do break down. There's lots of durability considerations. So lots and lots of technologies, both on the hardware side and the software side. And again, we're seeing the same thing where you have the gearbox design, and then you've got to go ahead and you have to look at all the different rule cases, everything from CFD to NVH to durability to multi-body dynamics, composites, structural engineering, lots and lots of the typical technology that we use in CAE applied to wind. But like I said, very, very high number of studies are required. And then the manufacturing of this really needs to be done well. So again, you have this feedback loop with manufacturing, and that includes actually the manufacturing process from a hardware standpoint and data acquisition, but also in the simulation of manufacturing. And finally, for the life of the service, and I'm using this term enterprise asset management. Service life, there's lots and lots of different technologies, and you can bring them back, and you can improve the designs. You can go ahead and automate the service and go from there. And that's really the autonomous aspect. So let's talk a little bit about virtual manufacturing now. So like I said, it's incredible penetration at the computational methods. Undisputed. It's really become an integral business process. It's essential to business. There's no company that does not use CAE that's doing anything that's advanced, period. It's amazing how much it's gone in the last 30 years. What computational methods haven't been used as much for is in the area of manufacturing. That would be sort of second place. And finally, in operations and looking at operations. Those are things that are really just beginning to realize their potential. And there's tremendous opportunity. And a lot of those kinds of applications are going to be mixed with data. So we shouldn't look at data and data science as being separate. It's something that we should embrace as mechanicians, as areas of computational science. We can this potential. Let's look a little bit. I'm going to run through really quickly here. I think some of you may not really look at all the different applications. One of the most interesting things about manufacturing is the people that are involved in manufacturing do not usually have backgrounds that design people have. They're not going to understand final elements. They're not going to understand actually. And this is a place where democratization, one of the reasons it hasn't really reached potential, is because you can't really get to the personas that actually use the software. So it's essential that you verticalize, democratize that makes sure things are robust, they just work, they get the answers, and they get to the point. It's actually a lot easier to verticalize this than a typical design application. Every company has a different way of design. You can't, as a tool provider, provide something. They have to customize it. But in manufacturing, it's a physical process. So it's a lot easier to verticalize. But very, very important. So you see some typical applications, bolt tightening, superplastic forming, extrusion, some eye candy there. Let me just sort of run through now some of the things that obviously are related that are multi-physics. This is actually curing simulations. So this is like baking a car when you make a car. Obviously, it's great to see a problem. So you go ahead and you can understand the flow and the temperature distribution, which then you use with your curing models as a sequential sort of step to be able to optimize the injection point, the jet velocity, and so on. This is actually a heat spring simulation. So here we're using a CFD, we're using multiplier dynamics, all together. And here we're going ahead and we're simulating manufacturing environment. And this is really important to be able to understand what's going on, manage the costs, the environmental pollution impact, and the different processes in manufacturing, like HVAC filters, looking at particulates. These are the kinds of things that are not state of the art for CFD, but now we can simulate those kind of things and people can make the appropriate improvements. Real fast here, it's just a lightning round. Sheet forming. I mean, this has been something people have been using simulation now for more than 20 years, 25 years. The new machine around even the early 90s, maybe it's even 30 years. It's a fairly mature discipline. So now it's about making the software easy to use and bringing it to the right personas, right? So with sheet forming and stamping, we have those. A lot of it is something rolling things up to be able to create costs, to be able to reduce the amount of waste. So it's not just the mechanics problem here. It's a lot about process planning and being able to model all these different scenarios and making sure that I can stamp as many things out of the same sheet. And now they used to go ahead and stamp these things and put them in a pile and then use the next station. Now it's just a continuous line in a lot of cases that they do. So the software and the tools have to sort of keep up with that, but it's pretty standard practice now. In a sort of deference to Dr. Mindlin, shell theory can only get you so far. So in the pure sheet stamping cases, shell theory is very adequate for, but there's lots and lots of form processes that require three-dimensional model, right? Including things where you're roll forming and other aspects, those sorts of things. Again, bring them up to the level of a practitioner in manufacturing to make them easy to use. Classic bulk forming. This was 30 years ago. You saw the first software to be able to do these kinds of applications. Now it's pretty much standard practice for things like forging, hot forging, all kinds of different bulk forming, extrusion operations. And what you need to do is have tools that are verticalized that a manufacturing engineer can use to simulate these things and get useful results out of it. And also, even for a designer to be able to make sure that he's designing something, he or she, that can be used, that can be manufactured. So there's actually a few different personas that need to be involved here, but the software needs to be tailored for that. It needs to be robust and verticalized. Virtual assembly, another really a big problem, right? Basically, connections could be anything from rivets and spot welds to welding. Interestingly enough, welding has been around for a long time. Simulation tools have been around for welding. Welding looks a lot like some of the new additive manufacturing processes, like directed energy deposition. Sort of from the physical algorithm standpoint, they're very similar. Obviously, the science and the detailed mechanics might be a little bit different, but the same kind of tooling can be used in kinds of cases, right? Then on the additive side, lots and lots of people, lots and lots of software vendors, organizations, academics have been working at solutions for additive at all the different scales, and the software providers have been trying to keep up with solutions for that aspect. Here, I'm talking a little bit more about specific applications. You'd be surprised how many kinds of manufacturing aspects there are to even producing battery boxes. You can include things, you know, and the same with the batteries. So usually you break down for electric vehicles. You have things, you have engineering at the cell level, which is the battery itself, at the module level, which is the group of batteries, and then at the pack level, right? So here's some examples of manufacturing at the cell level, right? This is actually a rectangular battery with cold forming, riveting, lid stamping, adhesive. This is got a life of its own here. Okay, so all right, so okay, all right, so we're good. All right, so I'd like to give a particular case here of some of the challenges we face in computation for additive manufacturing. This is actually DED. This is becoming now a pretty popular process. The powder bed fusion was the first one to sort of really get, but now DED is much bigger, and now people are looking at actually using direct energy deposition for very, very large parts. Amazing scale here. Not an easy problem to do, because if you go ahead and you want to track track the tooling on its path, becomes a multi-scale problem, not only in space but in time. Okay, because you can really, the number of increments can really add up. So you need to be able to use averaging methods and other techniques to be able to solve the problem. And in fact, that's exactly what, as the tool providers, we have done, is provide a variety of solutions. One of the goals when you're developing additive manufacturing software, make sure that the turnaround time is less than the actual print time. Now, in theory, you're going to gain more from a simulation than you're going to gain from a hardware test, but that's sort of the goal. So we need to come up with techniques to make those things fast. Let me skip ahead. Okay, so all right. So now I'm going to want to talk a little bit about AI meeting physics-based modeling. So let's talk about AI and the kinds of things you can do with AI for additive manufacturing, since we're talking about additive manufacturing. So the value proposition here is to accelerate the generation of data. So it's very interesting because it's kind of like a circle. You can use simulation to be able to generate data, and you can use AI models to be able to generate data. They're pretty from simulations. It really can come around. You have to be careful that it's not a circular dependency where you're not actually getting anything out of it, but it's kind of interesting how it does become circular. So it can be used as a way to accelerate the generation of data. It also can be used to simplify very complex studies. You still need to find ways of optimally parameterizing data. Boiling the problem down. AI ML is very specific. So a lot of engineering. In fact, for data scientists, I was really glad to see that now Columbia is getting data science, now a data science program. It's wonderful. The need for data scientists is out there. It's crazy. But data scientists that actually understand the domain are the most valuable. Because when they can combine a domain knowledge with data science, that's when they're cooking fast. There are lots and lots of opportunities for the young people in this area. And then also to be able to optimize, right? When you can build reduced order models, and they really can be effective, you can do all kinds of things with reliability, uncertainty quantification, and optimization. And so I'm going to look at, this was actually a project that was done with NIAR by our materials team, and they basically were looking at 3 levels. And the first one is the specimen level, right? And the second is the micromechanics level, with of course folks like Jacob are very aware of and have really developed outstanding and very effective methods in. And finally, the structural level. So these levels can play with each other, just like multi-scale. So on the at the specimen level, you have using AI, right? You can go ahead and set up your experiments. You can build a high-fidelity experimental testing regime, prepare the data, feed that into an AI model, and be able to then, separate your data into training and data sets. Build that model, and then you can go ahead and you can generate all the results you need to specimen using that qualified model. So that's the specimen level. Generate what's actually happening at the specimen level. Then you can, now in order to do that, you need to, like I said, you need to be able to parameterize models. So you could just go ahead and look at something as simple as a stress strain curve, have a certain points, and use brute force neural network and try to get something out of it. But it's much better if you can find ways of simplifying the problem with something that's practical, using the machine learning methods to be able to predict those kinds of things. So then we can go to the micromechanics level, and now we can use those specimen level results to be able to back out and reverse engineer those micromechanics properties. Those are always very difficult to find. That's where you can use AI from results that you have and feed them into a mechanics model using micromechanics and multi-scale methods, which can then be used at the system level or the structural level, right? So that's the last one I want to talk about here, which then once you have those the specimen level, you can develop your micromechanics, and you can use concurrent multi-scale or even use that to train phenomenological models and be able to do things at scale, right? And finally, you can use AI again at that structure level by creating lines that then at that structure level you can use for optimization using those parts in the performance conditions that you're looking at, right? So literally, data science can be used at every level here with just a simple additive manufacturing example. I want to kind of conclude on a little bit about sustainability, okay, before I end here. So this is something that I think it's been of the last 2 years, it's been a pretty big drive. I mean, the thing about sustainability is it's a real problem that we have. Our Earth, we don't have 2 Earths, we only have one. It's not really up to the politicians in the SME, it's up to technology, it's up to engineers, and it's a combination of government, universities, industry. Everybody has to be involved. Our young people are aware of this, so that's a start. There's lots and lots of awareness, but really, I think technology is going to bring us through. And sustainability isn't only about the Earth, it's also about economic sustainability. Things have to come together, and I believe technology is the thing that's going to do it. So now, sustainability means a lot of things to different people. Just a cartoon, right? It depends on where you're coming from. This is a Gro Harem. She was the first female prime minister of Norway. Sustainable development is the development that meets the needs of the present without compromising the ability of future generations. I'm showing it to you. Okay, so what are we doing with sustainability? Well, so we have all these different kinds of technologies on the hardware side, on the sensing side, and trying to bring things together, trying to provide things that are autonomous for the world and real world. But if we just rely on our customers to do this, we're not really going to understand what we need to do. So we actually spawned a company. I don't think this is, maybe it was in the making for a longer than this, but I'm sure this is not more than a year old. We had a solar farm, right, in a very, very nice place in the state, right adjacent to the Plaza, which I gotta go there because it's a great food battle. I find a way to get it. But basically what we're doing is we're coming up with a solar farm and we're going ahead and exploring everything that we can do for a time. From the construction of that farm all the way to the design, the construction, and the operation, everything, using all of the kinds of assets and things that we can bring to the table and learn how they can be used together. So these are the different kinds of things you can do with planning and build and different kind of eye chart exam here. Lots and lots of different measuring and simulation things that can be part of this autonomous system that we're trying to operate. This is actually these are actually live pictures, dashboards that we have. We have instruments with LiDAR, with cameras, with sensors. We can pick up exactly what's going on at any given time, right? And the goal of this was to basically take a typical like solar arrangement, make it a little bit more typical one, but try to get a 30% increase in efficiency just by employing these ideas of data, simulation, computational science, and autonomy. So this is actually, well, it was a live picture. It's not live here, but this is the kind of thing that we can see. This is actually a future farm here. It's another parcel of this one that's existing on the south. These are some of the things that you have with some of the issues that you have to do with engineering. Actually quite a lot of engineering, besides the usual thing about being able to get energy efficiency. You have issues with wind, you have storms and hail and snow. You've got things like vegetation you can see there. All kinds of things that can happen in addition to things that might be more related to systems itself, like things that could happen on an electric vehicle. Things aren't going to fry. Lots and lots of interesting engineering problems to solve. Because we're using our geospatial assets to be able to scan the geometry, we're using our CAD assets to be able to have a full 3D of the actual equipment itself, and lots and lots of other systems. So for CFD, which I'm going to highlight here, we have that visualization of the actual ground itself. And we can do CFD simulation, so we can understand what's going on from the standpoint of energy, wind, and sort of the efficiency of the system. So let me just click through a little bit here. Interest of time. So this is another example where we're using AI. This is something that we feel pretty comfortable with these days. We're able to come up with reduced order models for CFD. And it's using what I would call shallow learning. Maybe that's a silly term. More not neural networks. Not but other kinds of methods that we use to get reduced models, and we were able to go ahead and run real cases that might take hours to run, usually hours to run, come up with the data, and then be able to build reduced order models that really can be attributed to predict things in seconds. So we know to adjust these panels. We know based on road speed exactly what's happening from a footprint. And here I want to end on a note here, because this is also, we're at the state of the art. You think about virtual reality, okay? You think about heavy equipment. It's actually an iPad, just walking around with an iPad. But the iPad, because of the geospatial positioning, knows exactly where you are as you walk through, and you can virtualize exactly what you're seeing. So you do this whether you're in an industrial facility or in a factory, and you walk around the actual solar farm and on the ground and be able to see what's going on with it. So I mean, there's probably things that are more dramatic out there today, but this is now becoming the state of the art in industrial tools. It's kind of fun. So I wanted to finish with a nice animation background. And yeah, so just one more thing here. Typical scenario, windy day, it's predicted tomorrow, remote control room, everything is visual. You can look at it from another part of the world, and you can operate the farm. You can using your operational digital twin, be able to understand exactly what's going on in the farm, and then be able to make some decisions on what to do to fix the problem. So I think I'm getting toward the end here. I hope this was entertaining for you all. I know I covered a pretty wide scope, lots and lots of base vectors. Kind of went pretty broad, maybe not so deep. I know that I'm going to be meeting with a number of the faculty here. I'm very excited to do that. Maybe then we could go a little bit deeper. But I thought that I just wanted to kind of, my main thing today was really, and I guess if I was just going to say one message here, is if you think about where we are with computational mechanics and computational science, things have matured a lot over the last 35 years from the time that Jacob and I went to school together. But there is so much opportunity. There's an incredible amount of opportunity. I want our people after I'm retired and Jacob's retired. There's lots and lots of opportunities to really change the world. And that's why I'm working on sustainability. It's about products, it's about things that are going to affect their lives and make the world a better place.
Our teachers, the teachers operate actually also affect the operating how often that is updated.
Okay, so that's a actually that's a really good point because let's be serious. You know, I threw that picture up of Manhattan, right? Okay, so digital twin is going to be, let's say it's a reduced order model.
Yeah.
Let's say I have a reduced order model that can map out of tolerance geometry, and I put that in there. And all of a sudden, a guy upstream says, you know what, I'm going to change the part rule. And I go ahead and change it. And that digital twin is completely outdated. I mean, let's see what happens. So actually, one of the things that what I believe, and I think what we're trying to do with our company and what others are trying to do, is it's going to be really important. The other word that's used with digital twin is digital threat. Again, these are kind of big terms, whatever the heights are. But the digital threat to me is when I can connect things. So I know that when I do a design change, something in the macro, that I know that twin's out of date. And for instance, if I have an automated workflow, let's say data science has had a pretty good. Data science has had a pretty good. It's hard work. You got to parameterize things. You got to figure out what machine learning models you want to use and all that. But if you can automate that process, then when something goes ahead upstream and changes a part, then you can go ahead and hopefully run that through again and update that data. So we're not there yet. I mean, so many disconnected systems, and I think until you can do that, it's very likely that you're going to run into that catfish problem, and the digital twins will not be able to update. But in that case, if you can do automation, and then you cloud say, so you have unlimited resources, you should be able to update those twins. Even if you have to run more training data on real simulations, right? You should be able to update those data.
I think that when operating the twins, we constantly obviously have data that can provide you do you have a static?
Yeah, no, so that would be, yeah, so that's the other thing. So I mean, digital twin would be used for so many things, but and I didn't talk about that much, but obviously it's kind of like reinforced learning or something, right? So there's a huge opportunity. There's a huge opportunity to even update our computational models, what we call digital twins, right? I mean, there's so many uncertainties, especially when it comes to the closure equations, right? The materials. Who knows, right? And I think those are the kind of things that there's a huge amount of opportunity. So part of it is the science, data, mechanics, and also software. You know, we have to have systems that can make sure that we get that, we take that data and actually get those updates. And in production, we need that sort of happen on that. Can't be done.
Thank you very much for a very nice presentation. Clearly, data science and AI are going up and picking up strongly in the last decade or so, especially recently. But I have a feeling that the mechanics side is kind of going down. And people think that data science can essentially replace mechanics at some point. But I think that this is kind of, you showed several examples where mechanics is important. but it looks like the data science is more important than mechanics.
Yeah, I know, and that's true. My belief is, and I'm going to share. I had a friend pass away, Alex Vanderbilt, who was sort of the person that was my go-to person for data science, right where I used to work. And he said, whatever you can do with physics-based modeling, you should never do with data. It's only when, because you can always, even with data, when I showed you that stress strain curve, what did I have to do? It wasn't like I just threw numbers at it and you got it out of it. I actually had to take the stress strain curve, which is the fundamental understanding, right? It's a way of and parameterized. It wasn't parameterized because it was polymer, but maybe had 5 parameters, right? And I had all these kind of inputs like manufacturing things. And eventually I did that. But I needed the mechanics to even understand. So I think that things, I think simulation, first of all, can be used in a lot of ways. One, it needs to be used for basic understanding. When you talk about things like reliability or uncertainty quantification, I think we're still gonna have to go to reduced order models. Otherwise, Amazon and Microsoft and Google are gonna get really rich. They're already getting rich with cloud computing. But I think that when it comes to being able to do these vast studies where you're okay with approximation, I think you're going to need shorter models. But I don't think the need for the physics is going to go away. The other thing is, and even companies like, let's say, Unreal or Unity, right? That kind of software that's more gaming, right? They're looking right now at opportunities where you can go ahead and basically create synthetic data. This data's got to come in data science to train these things. And simulation can be basically to create synthetic data, just like the instrumentation. So I think we need to embrace it. I think there's still so much more to do. And if you don't have that physics understanding, a neural network's not gonna do anything for it. If you don't, it's what you don't understand with physics. That's when we can do things like unsupervised learning and learn new things. It's great. So I think they go together. But to me, things that you can do with physics, when it's worth it, it's not going to go away. There's plenty of things that you know with physics and optimization and generative design and all of these things. So I don't see it going away. It's going to be a problem that our kids are going to have to solve. I know it's not going to go away in my lifetime, but I think there's still more to do.
Perfect, thank you.
So I love broad swath that you took this lecture. I want to make one comment. I truly believe when you want to try to link to manufacturing and ophthalmology, it's all going to be reduced order models with uncertain quantification. The second thing, though, you talking about software in the hands of designers and you optimize those designs for chip manufacturing. And it's difficult for the mechanician to be here because they're kind of siloed things.
Correct.
But when you show the example of Hexagon's investment in the solar photovoltaic plant, I thought that's really interesting because now, you don't have silos. You're trying to operate a solar facility and learn from that solar facility.
And there's a lot of things that come together. You have to break all the silos.
And so is that something?
Yes, I think that it's a trend. I think Hexagon is doing that, and we're really taking the next step. We have, to be frank, we have lots and lots of really good technologies, and we haven't done enough to bring it together. And that's one of the reasons we did this. Was we're understanding how to bring them together, but it has to be done. So the best way to learn that is to operate something yourself, right?
Fantastic idea. See this being template other solutions.
Right. No, and I think that in general, with even the large PLM companies and others in our space, that the trend is trying to provide a solution that combines things. It's a holy grail. There's a way to get there. It's a journey, but I think everybody's trying to.
you showed that example regarding what you just mentioned on the device that is kind of the digital twin of a smaller device. I know that this is kind of the same, but at a smaller scale.
Yeah. Well,
You have like a laboratory device, you can optimize it. And then you have this big, solar panel.
it's a matter of scale. It really is. And we take it multi-scale now and we really generalize it to something that goes way beyond materials, right? It becomes a scale. Yeah.
Thanks for good. I have a question from the production. So the graphical CAD framework, especially for measurement, is not like the scalability of that process is not similar to data. But I think we have some problem to run like APM on GPU.
Yes.
But the data science cycle use GPU heavy.
Correct.
So there is like some mismatch from the scalability point of view. How do you cycle?
There is. So I think that, so GPU, there's lots of other people that can probably make better predictions than me, but right now with the classical methods like FEM, CFD, whether it's finite volume or finite element or edge elements and electromagnetics, it doesn't really matter. GPU will only get so far. Now that doesn't mean that it's not going to improve. I mean, you're looking at what NVIDIA is doing now with ARM. They're starting to do what they have a price for ARM now, and they're combining it with their GPU. So who knows what's going to happen? We can be, but I think that for the time being, the typical discretization methods that we use are best done massively parallel. And what really we have now though is with cloud, and whether it's private cloud or public cloud, or it can be private cloud, it can be private state, you have the ability to scale. So I think scaling probably does. Now, sometimes GPU can help. I can tell you, like, my experience is when you're solving like linear equation systems, very, very large linear equation systems, GPU can give you a boost of maybe 2 or 3, but it's not 100, right? It gives you a little bit more. You're going to be much better scaling out. And I don't know that that's going to change. I mean, really, gaming was the first driver for GPU, obviously. It's huge. And now data science is the big driver. That's why NVIDIA probably makes more money than God right now, right? It's incredible how much it's growing. But I don't see that really. I don't know if it's going to be breakthrough, but like I said, it's maybe that when who knows what people are going to develop in the future. I think the current GPUs though can only do so much for the traditional kind of computational stuff.
Any other questions? Then I will just thank you.